Okay, so now we'll talk a little bit about how lenses work. So as you can see, I'm wearing glasses, and these glasses bend the light or refract the light to be able to help correct some of the errors that I have in my eyes. So we have many applications of lenses. Today we're going to be talking a little bit about optical projection. So you've seen in movie theaters, there's a projector at the back of the theater, and there's an image that's in the image chip that goes through lenses, and the operator adjusts these lenses so that you create an image that's focused a far distance away on your movie screen. And the image is very magnified, so you see a very large picture, and the object itself, though, is very small. So let's first talk a little bit about how the lens works. So in order to talk about the lens, we first have to draw what's known as the optical axis. So the optical axis passes through the center of the lens. So we're going to have a lens here, and I'm going to draw it. My lens is going to cut off at the top, but this is the center or the widest part of the lens, and then the rest of the lens just extends off to the top. And I'll explain a little bit why I drew this a little bit asymmetric, but this is the very center of the lens. So what a lens does, so imagine that we have the sun very, very far away, and so we have rays of light, and what the lens is going to do is it's going to focus this light to a point. So the light that's coming into the lens parallel to the optical axis focuses to a point at a distance f away from the center of the lens. So this distance is f. Similarly, if we had light source from the opposite side, this would focus to a point that's the same distance away, f, on the opposite side. So that's my focal properties of the lens. So now we want to see, how does the projector take the image from the chip that's being displayed. So you have like a 1-inch chip, and then you project and you get several feet tall object, or image. So we have our object, which is the thing that we're displaying. And so just imagine that it's a person standing up, smiley face, and the image that's being formed, we analyze it by looking at the different rays of light that that the sunlight is illuminating the person, and they go through the lens. So what we just said is that if I have a ray of light that's parallel to the optical axis, so I'm going to put one arrow here, so these things are parallel. So if I have this ray of light that's going parallel to the optical axis, when it gets to the center of the lens, it's going to bend and go through the focus f. So that's going to be one of the rays of light. Similarly, we said that, so this ray is going from left to right. If we have a ray that's going the opposite direction, it'll pass through the focus. So just imagine I have a mirror here. So if I were to send a ray of light going this way, then when it goes to this lens, it should come out parallel. So now, the other ray that we want to draw is what happens to the ray that goes to the center of the lens. So a ray that goes to the center of the lens doesn't bend at all. So the angle from this curved surface is such that it's at normal incidence, meaning that it's at a right angle. And this will go through the lens unrefracted, so it won't bend at all. And so where these three rays meet is where the image is going to form. So you notice that the person's top of their head is going to be down here. So this is the top of the person's head. So the other thing to notice is the feet, they're on the optical axis. So if I draw a ray that goes through the center of the lens, it's unbent. If I draw through something that goes through the focus, it comes out parallel to the optical axis. So all the rays that are coming from the foot all end up over here. So we're going to get the person's foot at the optical axis, and then their body is going to be like this, and their head is going to be upside down. I've run out of space a little bit, so their head is a little bit compressed. So this is how we take the object and we form an image, and you notice that the image is magnified. So we wanted to be able to talk about the relationship between the object distance O and the height of the person h, and the image distance I and the height h prime. So we want to be able to calculate these quantities. And it looks like Yeah, so the height h prime. It looks like my writing is a little bit off the edge of the board. Okay, so what we need to do is we need to look at similar triangles. So there are many triangles in this figure. I'm going to label some points. So this is going to be my point A. This point is going to be B. This point is C. It's the center of the lens. And then I have a corresponding point A prime, where the person's head started. It ends at A prime. I'm going to have B prime, which is where their feet ended up. And then I'm going to have C. I'm going to label this point up here as D. And then I'm going to label this point here as E. And then finally, I'm going to label this point here as F. Oh, looks like I did it backwards. I want this point to be D and this point to be F to match with the worksheet that you'll be able to see. So now we want to look at certain triangles. So some things to note. This triangle here, this is a right triangle. So there's a right angle here. So we want to find a triangle that's similar to this triangle. It turns out that this triangle is similar to that triangle. And the way that they're similar is that we first look at this angle, which I'm going to put a single dash to indicate that these two angles are the same. So these two angles are congruent because we have a pair of intersecting lines. We know that this angle plus whatever this angle happens to be is 180. This angle plus whatever this angle is 180. Therefore, these two angles are congruent to each other. They're equal because of this vertical angle relationship. So from this, we can see that these two angles are equal. We have a right angle and a right angle. Therefore, this third angle here and this third angle here, they have to be the same. So I'm going to put two dashed marks. They have to be the same because the sum of the three angles is 180 degrees. So what I can write is I can write that triangle ABC is similar to triangle, so A is where the head is. It's similar to triangle A prime, B prime, C. What that means, if I were to draw, so I have the first triangle, and this triangle has A, B, C. This is my right angle. This distance from B to C is the object distance O. The height of this triangle is the height of the person H. If I were to take this triangle and flip it so that it faces the same direction as this, so I flip it vertically and I flip it horizontally, that triangle would look like this, where I have A prime, B prime, C prime, or C prime is C, and the height, A prime, B prime, this is H prime. This distance from B prime to C, that distance is the image distance I. These two triangles are similar, meaning that their lengths are proportional. So I can calculate a quantity known as the magnification, and the magnification is equal to, well, this one is flipped, so the magnification is a negative number, so we put a minus sign first. The magnification is defined as negative the new height, the image height, h prime, divided by the source height or the object height, h. And because these triangles are similar, the ratio of h prime to h is the same as I to O. So I get negative I over O. So that tells us, I'm going to write it up here because we're going to need this later, the magnification, which is defined as h prime over h, this is, or negative h prime over h, this is negative I over O. So that is one way that we can figure out how big the object is. So again, with the example of the movie theater, this is the person on the computer chip that's inside the projector. This person is less than an inch tall. You project it onto a screen, the person shows up as 5 inches, or not 5 inches, but 5 feet. And so what you are doing, notice that this is upside down. So either the chip has to have the image flipped, or you need a pair of lenses to invert this relationship so that the person appears standing up. Okay, so now what we want to do, so right now we know that the magnification in terms of I and O. The problem is we don't know what the image distance is for a given object distance. So we need a second set of similar triangles in order to figure that out. So I'm going to draw one specific triangle, and I'm going to ask you to think about what are triangles that are similar to it. So the triangle that I want you to think about is this triangle. So this triangle, so the question I want to ask is, what is similar to triangle DCE? So we want to find a triangle that's similar to DCE. And I'm going to just give you like a moment or two to look. There's actually two triangles that are similar to triangle DCE. And I'm going to draw some of these things a little bit darker so that you can see all the triangles that are possibly involved. So there's like this line, and then there's this line, and so forth. Okay. So in order for us to have similar triangles, so I'll let you think about it a little bit, but in order for us to have similar triangles, we need the three angles to be the same for one triangle to another. So we need angle, angle, angle for us to say that these two triangles are similar. So we have, in this triangle, we have one right angle. So we need to find triangles where one of the angles is a right angle. The other thing we need to do is we need to find angles where we know that this angle is the same as something else, or that this angle is the same as something else. So I'm going to first do the case where we can just see by observation that these two also form vertical angles. So I'm going to label this with 3 marks and this with 3 marks. And we can see that triangle DCE is similar to triangle ABE. So triangle ABE is one answer, because if I look at ABE, this is a right angle, DCE, this is a right angle, and then when I go BEA, then this angle is corresponding to CED. So those two triangles are similar, and that's enough for me to be able to derive the equation that I want, which is to get the image distance in terms of the object distance. There's another one which is actually a little bit easier to work with, and hopefully you've seen the other triangle. So the other triangle that's similar is this one. So triangle DCE is similar to triangle DFA. And you can see that this angle, it's shared by both of the triangles. So DCE and DFA, this has the same angle in both. So I'm going to label this as 4 marks. And then this right angle, those two are the corresponding, the two angles that are congruent to each other. And then this angle is going to be the same as this angle. So I can mark it with 3 marks. So this is a shared angle for both of the triangles. These are both right angles, so the remaining angle has to be the same. And you can also get this because this line is parallel to this, therefore this angle and this angle have to be the same. I can't remember if this is exterior or interior angles, but these two angles are the same because these lines are parallel. Okay, so we're going to use the second set of congruencies. We're going to say, or similarities, the triangle DCE similar to triangle DFA in order for us to get the equation that we're looking for. So if I draw triangle DCE out here, I know that this distance from C to E, that's the focal length F. And the distance from D to C, from here to here, that's the height. It's the same as the distance from A prime to B prime. So this is the new height, H prime. The other triangle, which is bigger, this distance from F to A, this is the object distance, O. And this vertical distance, it's going to be the distance from D to F. So that's this distance H prime plus the distance H. So this is H prime plus H. So now I can write the proportionality. I can write H prime plus H is to H prime. So this length is to this, as O is to F. And so now I can simplify this. So H prime over H prime, that's 1, plus H over H prime is equal to O over F. Now, we already calculated the ratio of h to h prime. Actually, we calculated the ratio of h prime to h. This ratio, h prime to h, is I to O. So if I continue that, if h prime to h is I over O, then h to h prime is O over I. So I can write this as 1 plus O over I is equal to O over F. So my final step is I'm going to divide both sides of the equation by the object distance O, and I'm going to get my final answer, which says that 1 over O plus 1 over I equals 1 over F. This is known as the thin lens equation, and it allows us to calculate how far away the image forms if we know the focal length of the lens F, and if we know how far we've placed the object from the center of the lens O. So this allows us to calculate the image distance I, and then we can use the magnification equation to calculate how big the object is going to be. So let's do a few examples just to see sort of what's going on in terms of approximate dimensions. So we have in your projector kit, in your project, you're going to be working with lenses where the focal length is equal to 10 centimeters. So 10 centimeters is about 4 inches. So each one of the digits on your finger, or each part of your finger, each segment is 1 inch. So your focal length is going to be about 4 inches, so about that much. So we want to create a table. So we have the object distance, the image distance. So I'm going to pick, based on this equation and the way that I've drawn this, every time I've drawn this, the object distance is greater than the focal length F. And the image distance is also greater than the focal length F. So we're assuming initially that the object distance and the image distance are both greater than F. I'll talk briefly at the end as to what happens if I place the object at a distance closer than F. It's actually very interesting. But let's just assume now that the object and the image are less than F. And we're going to create a table where we also calculate the magnification. So let's pick an object distance of 12. And with this object distance of 12, what we're going to get is that the image distance is going to be 60. So you just plug into this equation that O is equal to 12 and F is equal to 10, and you solve for the image distance. And you're going to get that the magnification is -5. If you plug in 15, you're going to get 30, and the magnification is going to be -2. If you plug in 18, this is going to be 22.5. So I picked nice round numbers so that we get a good result. So you get -1.25. There's a very important case when I set the object distance equal to twice the focal length. What happens is the image distance is equal to the object distance. So both of these are 20. And I get a magnification of -1, which means that if I have a 1 inch object here and I go through this lens, I'm going to produce a 1 inch object on the image. So this is just going to relay the image from one location to another. And this equation, it's interchangeable in O and I. So I can see that the I of 22.5, if I put that as the object, it'll create an image distance of 18, and the magnification will be flipped. So this will be -0.8. And similarly, I can go down for 30, this is going to be 15, and you're going to get -0.5. And lastly, if I plug in 60, I'll get 12, and this is going to give me -0.2. So now I want to plot this just to see what this looks like. So if I plot the image distance as a function of the object distance, just so that you get practice with this, when I plug in the object is equal to 12, I get an image distance of 60. When I plug in the object distance equals 15, the value cuts in half to 30. When I plug in 18, so these are evenly spaced, I'm going to get 22.5. When I plug in 20, which is a little bit unevenly spaced, I'm going to get 20. So if I trace out the curve, I'm going to get this relationship, that this is sort of a 1 over O dependence. And so this is actually the shape of a hyperbola. So this is one way to plot the data. And what you're going to do when you build your system, you're going to adjust the distance the object is from the lens. And then you're going to measure how far away it forms an image. and you're going to graph the data to see does it agree with this, this equation. The other way that you can plot this is you can create a new variable. I'm going to call this x, which is equal to 1 over the object distance. And I'm going to create another variable y, which is equal to 1 over the image distance. And this equation says that y, which is 1 over I, this is equal to 1 over f minus 1 over o, so minus x. So this is an equation of the line, so let me rewrite this as negative x plus 1 over f. This is an equation of a line with slope -1 and intercept equal to 1 over f. So if f is 10, then this is going to have an intercept of 0.1. And then this equation is just negative x, so this is going to be 0.1. And with our object distances, we're always assuming that the object distance is larger than the focal length, so we're only plotting the part of the curve in here. So we get this line, and you can check out the points. Like this point where this was 12, this is 0.083, and this value is 1 over 60. So you can check that these other points that I've plotted in this graph, there's corresponding points in this equation. So you can use this graph where you plot the horizontal being 1 over the object distance and the vertical being 1 over the image distance, and you'll get a straight line. And this allows you to check how well your fit works. Some of the other things you can see when you plot it this way and you do a linear fit, you can figure out what the focal length of the lens is because it's going to be 1 over the intercept. If I have a different focal length lens, like if I have a longer focal length lens, this intercept would be smaller, and so I get graphs that look like this. So depending on the focal length of your lens, you'll get a different line, and similarly, depending on the focal length of the lens, these graphs would be different curves. So the goal is to be able to calculate these quantities by measuring it and then plotting it and then seeing whether it agrees with these equations. You can also write out the equations for the magnification, but I won't really get into that. So the last point I wanted to quickly just bring up is what happens if I place the object at a distance that is closer than the focal length of the lens. So let me just draw a small sketch at the side to see what happens. So this is the lens, this is the focal length f, I have this distance f. If I place the object here, what I want to see is what happens. Well, we're going to follow our same rules for ray tracing. A ray that goes parallel to the optical axis passes through the focus. A ray that goes through the center also passes through undeflected. And if I have a ray that's going in the opposite direction, it's going to come out, If I have a ray that's going through the focus, in this case it has to go this way through the focus, it'll come out horizontal. So my lens needs to be a little bit bigger. So the problem is when I look at these rays on this side, these rays are actually getting further apart. They're not going to come to a point like they did in this case. So therefore they're not going to form a real image on the right side of the lens. What will happen though is if we continue to trace these rays backwards and just look and see what happens, these rays will all intersect at a point over here. Not necessarily the focal spot. Let me move that focal spot a little bit. Not necessarily at the focal spot. And what I'll create is I'll create a virtual image of the person. So this virtual image is not actually visible. Like you can't actually do anything with this image directly. It's not created anywhere. This is only useful if I'm creating a compound imaging system. So if I put another lens here, then I take this virtual image and I use the ray tracing through this second lens, and maybe I create a real image on the right-hand side. So this could be the principle for how I do my projection, but now I need two lenses if I'm going to be working with this virtual image. The other thing that I wanted to mention with lenses, so we talked a little bit about how light comes in and it focuses to a point. So this is useful for making what are known as thermal-based photovoltaics. So the idea is that you concentrate the sun's light into, let's say, a cylinder. It's like I have a cylindrical rod like this, so I focus the light into the cylinder. And what that does is I can heat up an oil, and that oil can then drive or create steam, and I can drive a steam engine to generate electrical energy. There's another type of solar cell, or another type of way to convert from solar energy to electrical energy, and that's to use what's known as a solar cell, where you're directly converting using a semiconductor from the light energy directly into electrons and what are known as holes, and you generate the electricity or the energy in the electrical case by directly absorbing the light. This lens idea is useful if I want to focus to a point spot and create something very, very hot. So as a reminder, when you build your project, just be very careful not to put your lens anywhere near sunlight because it will focus light, and so it's a safety hazard. So with this, I hope you enjoy building your projector. Look at how the distance, when you change the object distance, how does that change the size of the image that you produce and where it creates its image. So thank you.